the stuff going in, if we look at the world line of what goes in, it effectively completes these Wilson lines into Wilson loops. Okay? Now, there are two ways in which this completion could happen. And these are the two different channels of scattering. One way it could happen is like this. And another way it could happen was like this. Okay? Now the important point is that if you complete the thing this way, and you complete it this way, the blue way and the green way differ by having either two factors of a spherical Wilson line, two factors of an unknotted Wilson line, or one copy. Okay? Now, if the rule is that you have to strip off the contributions of these Wilson lines, in computing S matrices. So the thing that is analytic is these things that you compute with dressing with the Wilson lines. Okay? But that tells you that the part without the dressing, the part that we actually compute, we don't have these Wilson lines. Okay? Should obey a crossing relation that goes like sine pi lambda by pi lambda squared times one of the S matrices, analytically continues to sine pi lambda by pi lambda times the other S matrix. Just because two copies of the Wilson line is sine pi lambda by pi lambda squared, and one copy of it is sine pi lambda by pi lambda. Cancelling the factor of sine pi lambda by pi lambda, going through it in detail, you produce exactly what we get. You produce the prediction, if you believe this heuristic argument, that sine pi lambda by pi lambda of the T-channel S matrix should analytically continue to the S channel, to the T-channel, I'm sorry. Sine pi lambda and pi lambda of particle-particle scattering should analytically continue to particle-antiparticle scattering with singlet exchange. Okay, so this is, admittedly a very heuristic argument. It's actually strongly motivated by arguments used by Witten in his classic Jones polynomial paper. I actually ran this argument by Witten, who said, I really like the argument, but I can't guarantee it's correct. I don't know what that means. Okay. So anyway, it's basically a heuristic argument. Okay? Just to give you a feel that there is some possible structure for explaining this. Okay.
The statement you want to make here is strictly for S matrix, not for correlators.
Yes, I want to make the statement only for.
And so for the LZ reduction, you need to take some limit in momentum space.
Right.
And that's not obvious from this picture. Exactly how do you understand that?
How do we understand that? Yeah, so one way of thinking of the LSC reduction is in position space. Right. You take a sphere, put insertions of points, and take the sphere to infinity while letting this point go along the trajectory of the world line. The free trajectory that would get there. That's equivalent to the LSZ picture in momentum space.
Yeah, but you need to kind of average over these, right? You have to do the Fourier transform. Right?
You have to do the Fourier transform. But this process completely produces that. This you can show, for instance. Right.
No, for the Wilson lines, in this case, somehow it's, the stuff that's attached outside is simple, but in a more complicated situation, you would worry about
winding.
So inside the sphere, which way they cross.
Very good, very good. That's actually very important. You see, the thing is this, that what we compute, the process, the dynamical process that we have computed, sums over all these ways of crossing. Right, that's basically what the dynamics does. That's the Aronoff-Bohm, the relativistic Aronoff-Bohm scattering. What we have to add in addition is what phase we are associating with the baseline. You see, there is just the process which is just doing nothing has an associated thing, and then everything else is being computed. So that's why I'm drawing only these base processes. Summing over all those other things is what we're doing. That's the dynamics of what's going on. Okay, that's the idea. But it's to deal with all of these things cleanly, which is why it's a heuristic argument. It's not a proof, But it's just a suggestion for this, that this is the reason what's going on. Actually, there is a, I could tell you about it later, but there are these things called quantum 6J symbols that probably enter the story at finite n and k. There's probably, okay, if what we're saying is correct, there is probably a rich, this is some crude large n version of a rich finite n, finite k statement, which clearly has some interesting connection with the mathematics of Chern Simons and Weissman-Witten theories. Okay, and this structure appears a lot in these quantum 6J symbols. I could tell you about later, but since I have no results of that, I won't. Okay, yes, I'm basically done. Yeah, okay, yeah. I just take 2 minutes and then.
No, I just have questions.
Yeah, yes, yes.
So this will be something that is universal, right?
Yes.
And I can expand that in coupling constant.
Yes.
So I can test this perturbatively.
You can test it perturbatively. Exactly, exactly. Yes. So in particular, you should find 2 loops. You see, the sign expansion has lambda and a lambda cube.
Yeah.
Okay. So there is a 2-loop check of this, of this thing. But you know, there is a simpler thing at 1 loop. The first thing is that you should produce the delta function. Okay. So this is a question at 1 loop because it's lambda square. Okay. Now this, with my students, have done a little. Okay, let me tell you. I did the following little calculation just to get a sanity check on that. It's all very subtle. Okay. You see, we wanted to work in some place where we could directly look at the particle-antiparticle scattering. Unfortunately, with our setup, we couldn't. Okay. So what we did was to just work in Lorentz gauge and just do the honest 1-loop calculation. Okay? In Landau gauge. Now, when we first did it, what we got was exactly, consistent with our conjecture, except we didn't see the delta function. Okay? But then we sort of thought about that to see why that was the case. And we realized that why it was the case was that following, your lead and so on, we were using these on-shell reduction formulas for Feynman diagrams. These on-shell reduction formulas that we were using fail at exceptional momenta. Okay, there are some manipulations that don't work at special momenta. And this delta function is triggered only at 1 momentum, namely forward. Turns out to be one of the places where it failed. So to do things better, what we did was the following. We stayed away from being on-shell. That is, we let these initial particles be on-shell. And this is something my students are still getting completely straight. We've not written it up yet. But okay. These initial particles are on-shell. These final particles, we allowed them to be off-shell, that is on-shell with a different effective mass. And then we looked at the scattering amplitude as a function of how far off-shell we were and of theta. Okay? And we got the same answer that when the off-shellness was small, we got the same answer that we got before, plus some number times square root, epsilon by epsilon squared plus theta squared. Where epsilon is how far off shell we went. Okay? So, if you first go on shell, you take epsilon to 0. It's just a 0. Consistent with what we got before. But if you keep epsilon fixed, and look at this has a huge bump and in fact integrates to a delta function with exactly the right coefficient. Okay? So there's something very subtle. Just to say again, this whole answer that we got was an analytic function of epsilon and theta everywhere except epsilon equal to theta equals 0. So there's something very subtle in this case about this one point, producing this delta function. Okay? This I think we at least largely understand in some way of, at least the clear statements be clear. We certainly understand that there is a subtlety about the statement that it's analytic. Okay, we certainly understand that. Okay, now doing 2 loops is beyond my technical abilities, but it's before breakfast for you, I know. Okay, last statement is a minute and then I've stopped. Okay, the last statement is, along with my students, I am now students and postdocs. We're doing a generalization of this project, partly to make contact with the supersymmetric literature, which I think is a good idea. So, There's a lot I haven't been able to tell you about the story. One of the things I haven't been able to tell you about is that there's a generalization to theories with both bosons and fermions. Now, we understand fully the duality on the manifold of theories with both bosons and fermions. But in particular, we understand that on the cut of theories, which is n equals 1 supersymmetric. Okay? So what we're doing is to work out the scattering calculation for n equals 1 supersymmetric theories. A technical tool that we use is that it's quite easy preserving n equals 1 supersymmetry to get a supersymmetric version of light cone gauge. One that preserves supersymmetry. And so we work in superfield language. We can redo all these calculations in superfield language. It all goes through. And we have computed the 3 easy channels. And we have checked that that agrees with duality. Okay, so we've done that. We're still trying to work out the unitarity issues here. Because there are some further complications. We're still trying to understand the unit, but hopefully that we will get straight rather soon. Okay. One thing that we've already noticed is that while we get answers of comparable complexity, being at the n equals 1 theory, the superfield stuff basically makes the calculation about as easy or difficult as it was for just scalars. Okay, it's neither more difficult, but a little disappointingly not more easy. Okay, you get comparably complicated formulas for the S matrix. However, there is a particular point in the n equals 1 space where the theory becomes n equals 2. And at that point, a dramatic collapse of the formula happens. So the n equals 2 theory is somehow very simple. Okay, certainly the n equals 6 theory will be as simple or simpler. We're trying to understand this. I won't report results because I'm not yet sure. We haven't done all the consistency checks and so on. But we're edging towards trying to understand trying to test these conjectures in a broader setting, one involving more theories, and trying to make contact with a supersymmetric literature that I know some of you have participated in. Okay, I'll stop here. I'm sorry I went over time.
We already had some questions and we're a little bit behind schedule. So, yeah, let's thank Shiraz again.